Record. Okay. Okay. Good. All right. So I'm just going to kind of approach this from the beginning and just, okay. Let's say I just walked up to it and I said, all right, I'm going to read this problem. So I got a 2-kilogram block hangs from a rubber cord being supported so that the cord is not stretched. All right. So maybe the first thing I'll do is draw that picture. So here's kind of the ceiling. Here's kind of this rubber cord. Here is this block of 2 kilograms. And I'll just kind of say it's being supported somehow. They don't really say how. I'll just kind of pretend it's my hand. But definitely it's unstretched. And then they go on to say the unstrength length of the cord is 0.5 meter. And the cord, for that matter, has a mass of 5 grams. Now, I'm going to point out that 5 grams is, let's see, 1%, a quarter of 1% of this one. So, and it would be reasonable somewhere along the line if I go, well, I'm not going to worry about the force of gravity on the rubber band here, rubber cord, but 2 kilograms, I got to consider the weight of that thing. That's, that's like almost 5 pounds.
The next in the textbook, I don't think it's scanned on the homework packet, but in the textbook, number 50, the next one is the exact same problem, but just with no numbers. Okay. And I actually tried that first, just to try it. And it does say little m is much less than big M. So I kind of went with that as well. Yeah.
Okay. So, all right. So I'll probably do that along the way. Then when it comes to weight and stuff, I'll consider this big block, but probably not the rubber band. Okay. That's 0.25%, way too small to make a significant difference. All right. So then they say the spring constant. So I'll put that over here. Spring constant is 100 newtons per meter. Okay. So just kind of doing that first big step, I like to say, read it slowly, read it a couple times, get an idea of what the physical picture here is. Okay, so we finally get to a question A. Okay, determine the tension of the cord when the block is at its lowest point. I would assume, I think that unless I skip the sentence reading back and forth, they're implying that you're supporting it and then you let it go. And so
it says the block is released and stops at the lowest point.
Oh, thank you. Yeah, I did skip when I put my eyes down. Okay, that's what I was missing. So the block is released and stops at its lowest point. Okay, so drawing that picture, I'm going to put a dotted line maybe to say, okay, this is where it was while my hand was supporting it. And then I let it go. And here's where you made a comment that, and I heard both, so I'm not sure which one you did, but you could approach this with energy, or you could approach this with forces.
I did both, actually.
Yeah. Okay. Yeah. Kind of sounded like it.
Yeah, because I did forces first, and I got that. I got an expression for the tension, which involved mg and kx, and x was just the distance that it fell. But then I used energy to get an expression for x in terms of m and g again.
All right. Yeah. Okay. So, all right. So let me go ahead. Maybe I'll do it the reverse order of what you just said. Let me look at the energy first. And so using the principle of conservation of energy, I like to say, okay, let's take the energy initial and equals energy final and say, all right, what energy do I have to work with? And so for this problem, I would say there's kinetic energy involved, there's gravitational potential energy, and there's also the elastic energy. And it looks like the kinetic energy is not part of the beginning or the end, but in the middle. So it won't even show up in this equation. But anyways, let's go to the beginning. So the beginning, I'll say your hand is holding it way up here. And maybe the first thing I'll do is call it MGY initial. And if you let me go ahead and just do symbols, as you said, you did number 50, which is symbols. I'll just leave it as symbols right now.
Okay.
But one of the things, just to kind of do a 121 review, is we need to define where y equals to 0. And that's one of the neat things we learned, is we can define it anywhere we want. And this equation hasn't defined it. So this derivation of this equation, we still have that freedom to pick y equals 0 wherever we want. Half of me wants to say, well, let's start y equal to 0 where we start. But then it goes negative. So the other half of me is saying, well, I don't really like negative numbers. So why don't I call down here y equals 0? But I'm going to pause and throw it back to you. Where would you like me to call y equals 0?
I called it the bottom at its lowest point, y equal to 0.
Okay.
Yeah.
So I'll follow that. I'm going to put a little mark in my diagram here and go, okay, I'm going to call the lowest point. And so this right here has some initial value, the value we don't really know yet. Okay, so that's its gravitational potential energy to start. It's not moving, so I'll put a 0 kinetic energy. And the spring isn't stretched, so I'll also put a 0 there. Okay, now over here, once we let it go, as it goes down, it loses potential energy. It gains elastic energy. I guess for a while, it gains kinetic energy, maybe to about the midway point, and then loses. In fact, it would be exactly the midway point. We could argue that it has to be exactly the midway point, but I'll pass on that argument for just a second. But so the kinetic energy increases, reaches its maximum, slows down, comes to a stop right here. And so I would say then when it gets to this point, it has no kinetic. And that's where we're calling y equals to 0. So I'm going to put a 0 for the potential energy. I'm going to put a 0 for the kinetic energy. And then I'm going to put a 1/2 kx squared. Although, here's where I need to be careful with my symbols, because traditionally we put an x here for the spring, meaning how far did it stretch, but that is also then this y initial. So these are actually the same numerical values. So recognizing that, I need to decide if I want to call them y's or x's, and maybe I'll just call them y's. Couldn't decide there. MG. Oh, and by the way, this M, I probably should put a capital M, because if you're, as you said, if you're doing number 50, they called the bigger mass the capital M, and the mass of
the block, basically.
Yeah, the mass of the block. So I want to make that clear. So that's a capital M if I'm doing symbols. Okay, and so then this is a 1/2, this is a K, and then this is a Y squared. And again, if I'm just doing symbols, I can now solve for what Y would be. So let's see, I'll cancel out a Y on each side, move the 2 to the other side, and this then would be my equation for the value of y when it reaches. And now I need to come back to the question. What am I trying to solve for? Determine the tension in the chord. Now, I'm going to go ahead, just because I'm doing 49, and grab my calculator. I know that I'll keep doing it in symbols because it sounded like you preferred that, and I will. But also, I'd like to have a number. So grabbing my calculator here, maybe see both here on the screen. I'll go 2 times, what was the mass up here? 2 kilograms. G is 9.8 and K was 100. All right. So this should stretch at about 39 centimeters. I'll write it in meters though. 0.392 meters. All right, so let me call that page 1 and go to page 2. Still working on A though. So now I'm going to get the tension. Determine the tension in the chord. Okay, and so, and as you said, I would be doing maybe a free body diagram here. And what's lifting up is the chord itself. So let me call tension in the chord. And what's pulling down is gravity.
Okay, that I think is where I made a mistake, because when I did my free body diagram, I said gravity pulls down, tension pulls up, but then I also had a third force pulling up, which I called minus kx, but that's just because they called,
Oh,
I don't know, I guess they said something about the chord having a spring constant, so I don't know. Now that I'm thinking about it.
okay, so this tension is kx.
Okay. That was where I went wrong. I said that there was a third force pulling up. So so when there's a tension in the chord and it can be treated or modeled as a spring with a spring constant, they're one and the same. Basically.
Yeah.
Okay, yeah. That's definitely where I messed up, because then when I solve for t, I plugged in, well, so x would be what you called y on the previous page. So when I plugged that in, I had an extra term. So I got 3 times mg instead of 2 times mg. That's where I went wrong.
Okay. Yeah. So, and if you don't mind, I'll just kind of race through this, I think.
Yeah.
Then, oh, and by the way, I'll backtrack. What I like to say when I'm teaching 121, or even now when I'm teaching this and I need to review it for people at 121, when you're doing the free body diagram, the forces are everything touching it plus gravity. So in this case, the only thing touching it is the chord. So there would be gravity and then one other thing.
Okay, that makes more sense. Yeah.
Okay, so then if I put in the symbols here, here's the K, and then if you remember, the Y from page 1 in terms of symbols was 2 mg over K. So 2 mg over K. The K's would cancel, and as you pointed out, it comes out to be 2 mg, which would be 2 times 2 times 9.8. Oh, which since K was just 100, it would be the same value with the decimal move. So 39.2 newtons would be the tension in the chord. So there's A. B says, what is the length of the chord in this stretch? Oh, so I guess we technically did that already.
Yeah, that one was pretty straightforward, because once you calculate y or x or whatever you call it, you add it to the.
Actually.
You already did it.
Yeah, I actually ended up doing that one first.
Yeah.
But okay. And then D, find the speed of the transverse wave in the chord if the block is held in this lower position. And I'm glad they say that, because it wouldn't want to stay there. This would, it would stretch down and start to, oscillate. But they're saying if it was held there, so maybe, coming back to our free body diagram, somebody else grabs it and pushes down on it so that the two forces down equal the force up, which we already know the force up. Oops. Getting a phone call. Let me cancel that. Okay. The force down you would have to put must be mg, because we just said that the force up from the tension in the chord would have to be 2 mg. So C's free body diagram would have to look something like this, where you would have gravity pushing down, you would have the chord pushing up, but you'd have to hold your hand on it with a force equal to the weight of the block to kind of hold it down there. That's really not necessary to actually solve this, but little nice discussion of physics anyways. So here it says, find the speed of the transverse wave. And so hopefully you saw this derivation of what is the speed of a wave on a string, all of our mechanical waves, their speed is determined by what we call an elastic property and an inertia property, and then the square root of that.
Mm-hmm.
So can't remember if I said anything in the video lecture, but I'd like to show during this chapter those waves on those rods, and the rods rock back and forth.
Mm. Yeah.
And I've got two sets. One of them, the rods are twice as long as the other ones. So one of them has a length L. The other one has a length of L over 2. And since the moment of inertia of a rod around its center is 1/12 ml squared, the longer one would be this equation. The shorter ones would then be an L over 2, which I'm going to write then as 1/4 of 1/12 ml squared. So the moment of inertia is 1/4 for the shorter ones compared to the longer one. And if you put a 1/4 here for the inertia effect, it puts a 4 up above it, and the square root of the 4 is 2. So by that, we conclude that the speed of the wave of the shorter rods is twice the speed of the longer ones. And anyways, I can't remember if I said anything in that particular lecture or not.
I don't think you did about the rod specifically, but I think I don't remember either if you said anything specific about that.
Yeah. So, but anyways, I guess I'm speaking of a bigger property, and you'll see this in sound waves when we get into 17. But there is in the numerator, there's all the elastic property, the part that would make it snap back. So if it's a string, it would be, the tension in the string, how hard is somebody pulling on it. And then, of course, this mu is the mass density of it. That's the inertia effect of a string. And I probably shouldn't have gone down this discussion of the rods because.
Well, I think you definitely mentioned that it was elastic over inertial, but I don't think you had the discussion about the rods.
Okay.
Yeah.
All right. So sticking very, I'll say specifically for a string, then the speed, again, I'll say it, the elastic property is the tension in the string, and the inertial property is the mass density. So in this case, we could put in the tension, which we just did in A, 39.2 newtons. And then the mass density would be its length. And now we need to come back. I think we have enough information to get its length. Let's see what they say. Oh, so unstretched was 1/2 meter. And then in the stretched position, we had another 0.392. And the whole thing was 5 grams. So I'm going to write this as 0.005 kilograms over a total length of, let me add those two together, the 0.5 and the 0.392. So that would be 0.892 meters. And just a little subtlety on the unit. So before I do the numbers, you'll notice that I quickly switched the grams to kilograms.
Right.
And that's because I knew what was inside of this Newton. Inside of that Newton is a kilogram meter per second squared. So when you divide it by a kilogram over a meter, kilograms would cancel off. The meter would come upstairs and become a meter squared over second squared. And so then when you take the square root, you're going to end up with meters per second. So the units work out appropriately, as they should, but they only do if you make sure you put your mass in kilograms when your tension is in newtons. All right, so there's the units, and so let me do maybe 2 steps here. I'll take the 39.2, and then down here would be the 0.005 over 0.892. So that would be 0.0056. So now I'll go ahead and take that 39.2, divide it by my last answer, and now take the square root of all of that, and I get a final answer of 83.6 meters per second. And
That
is
makes sense.
there a D? I know, no D.
Yeah, the part that was just messing me up was the free body diagram. I think I was just so used to, from physics 121, like calculating tension. You just do the free body diagram and you get T equals, maybe it's mg sine whatever, and then you get a number. And then the springs were a separate thing in 121, but now we're treating the chord as a spring, so they're one and the same. Yeah, I guess I just kind of blindly drew a third force in there.
Right. Then I just calling up the answer, and it looks like good. Looks like I got it right. Nice.
Cool. Well, thank you so much.
You bet.
I'll probably jump in on Friday though, because I'm about to attempt the last couple problems, which I recall you saying in the lecture are some of the hardest ones. So
Yeah. Okay.
Yeah.
Hey, I don't remember saying that, but I'm sure that's true. They start easy and get hard. Yeah.
Yeah. Yep.
Yeah.
All right. Well, thank you again.
Okay. Okay. My pleasure.
Have a good one.